Welcome all to today's lecture. Myself, Assistant Professor Tukur Gupta from Ajay Kumar Garg Engineering College. The subject that I am covering in these lectures is a microprocessor and microcontroller. Subject code is KEC 502 and this subject is being taught in 5th semester. The topic that I am covering is microcontroller architecture. In previous lecture, I have already shared the basic diagram, the block diagram of 8051. Some program counter, stack pointer details, and few registers, the details about the bank registers and all. Now, in this lecture, I'll be sharing some more features of 8051 architecture. So the first feature that I'm sharing today is special function registers, which we call the SFRs also. In 8051 microcontroller, there are certain registers which uses the RAM addresses from ATH to FFH, and they are meant for certain specific operations. These registers are called the special function registers. Some of these registers are bit addressable also. So this is very important. The list of SFRs and their functional names are given below. In these SFRs, some are related to input-output ports, that is P0, P1, P2 and P3, and some of them are meant for control operations, that is TCON, SCON, PCON. And the remaining are auxiliary SFRs in the sense that they don't directly configure the 8051. So let's see what are these special function registers. So this is a whole list of SFRs. As we can see here, accumulator, B register, program status word, stack pointer, that is SP, data pointer, that is data pointer low and data pointer high, 4 ports, P0, P1, P2, P3. So these are all special function registers and these are their corresponding addresses of location. Next is interrupt priority control register. Next, interrupt enable control register. Timer mode register, timer control register. Timer 0 higher byte, timer 0 lower byte. Timer 1 higher byte, timer 1 lower byte. SCON denotes serial control register. SBUF means serial buffer register. PCON means power control register. So this is the whole list of 20 SFRs which are available in 8051. The star indicating here this and this. So this means that these registers are bit addressable SFRs. Now we talk about the parallel input-output ports. So what are these parallel input-output ports? So I have already discussed in the previous lecture that in 8051 we are having 4 parallel ports. Each are having 8 lines, input-output lines. So total 32 input-output lines are available. So in these slides, we will discuss what are the details of these ports. Upon reset, all these ports are the output ports, and if we want to make them as the input ports, then we have to set their particular bit as high, or we can set the whole port as the high. So suppose I want to make the whole port as the output port, input port, then I have to give FF to the port. If I want to make a particular pin of the port as high, that is as input pin, then I have to give high to that pin using SETB instruction. So these two instructions are used to make the whole port as the input port, and this instruction is used to make a particular pin as the input pin. So when we talk about the port 0, it is an 8-bit port with dual purpose. What is its dual purpose? So if external memory is used, these port pins are used for the lower address byte, that is address and data byte. Otherwise, all bits of the port are either input or output. So unlike other ports, port 0 is not provided with the pull-up registers internally. So port 0 has to be connected to the pull-up registers like this, using the 8K of pull-up registers. So the 8051 is used to connect the lower order address and data bus. So 8051 multiplexes address and data through the port 0 to shape the pins. ALE indicates whether P0 has address or data. When ALE is 0, it provides data D0 to D7, and when ALE is 1, it provides address and data with the help of this latch. Now, when we talk about port 1, it occupies the total of 8 pins. It has no dual application and it is used as a simple input-output port. But unlike port 0, this port does not need any pull-up registers since all the pull-up registers are connected internally. Upon reset, port 1 is configured as the output port, and to configure it as an input port, port bits must be set, that is a high bit must be sent to all the port pins. This is normally done by the instruction SAT B. As I have already discussed, that if we want to make this port as a port input port, then we have to give FF to this port. So we can transfer this FF immediate data to port to accumulator, and the value of the accumulator is moved to the port 1. So in this way, this whole port is configured as the input port. Now, port 2, it's also an 8-bit parallel port. It can be used as the input or output port. Again, this port is provided with the internal pull-up registers and does not need any external pull-up registers. Upon reset, it is again configured as the output port, and to make it as an input port, again we have to send 1 to all the pins or to the corresponding pin which we want to make as the input pin. So what is the dual purpose of this port? The port 2 lines are associated with the higher order address lines A8 to A15 in systems based on 8051 or 8951 and so on. Port 2 is used as a simple input-output port, but in 8031, the base systems, port 2 is used along with the port 0 to provide the 16-bit address for the external memory. Since an 8031 is capable of accessing 64 bytes of external memory, it needs a path for the 16 bits of the address. So while P0 provides the lower 8 bits of address, but P2 provides the higher order address bus. So this is the dual purpose port. Port 3 is also an 8-bit parallel port with dual functions. The port pins can be used for input-output operations as well as for control operations. The details are shown here. So port 3 does not need any pull-up registers as they provided internally, similar to port 1 and port 2. Upon reset, port 3 is configured as output port, and again to make it as an input port, we have to give 1 to this port. So the alternate functions supported by this port are shown here. The 0th bit of port 3 is used as the receiver bit. First bit is used as the transmission bit. The second bit is used as the INT 0. Third bit is used as the INT 1. Fourth bit is used as the timer 0. Again timer 1. And the 6th and 7th are used as the write bit and the read bit respectively. So these are the special functions supported by the pins of this port 3. Now, next important feature of the architecture are the interrupts. And what is an interrupt? It's an external or internal event that disturbs the microcontroller to inform that a device needs its service. The program that is associated with the interrupt is called interrupt service routine. We call it as ISR or interrupt handler. So whenever the interrupt arrives in the system, first of all, the program control moves on to the new location, and the program related to that interrupt, or we can say the routine related to the interrupt, is saved at that particular location, and that routine is known as the interrupt service routine or the interrupt handler. So upon receiving the interrupt signal, these are the steps. First of all, the microcontroller finishes the current instruction. It saves the PC on the stack, jumps on to the fixed location in the memory depending on the type of the interrupt. Next, starts to execute the interrupt service routine until RETI is encountered. So whenever we write an interrupt service routine, at the end, RETI instruction has to be added to the routine to indicate the controller that it has to go back to the main routine. Upon executing the RETI, the microcontroller returns to the place where it was interrupted and get the pop PC from the stack. So the previous contents of this stack are popped up and the contents are stored in the program counter, which holds the memory location of the next instruction to be executed. So basically 8051 is having the 5 interrupts, that is timer 0 overflow, timer 1 overflow, external interrupt INT0, external interrupt 1, INT1, serial ports event, that is buffer full, buffer empty, etc. interrupt. Each interrupt has a specific place in code memory where the program execution begins. So we can see the corresponding address locations of these interrupt routines. So on reset, all these interrupts are disabled and do not respond to the microcontroller. These can be enabled by the software in order for the microcontroller to respond to them. This is done by the 8-bit register, and this register is known as the interrupt enable register. This is a register where the interrupts are enabled. So here EA bit. This is the global enable or disable bit. To enable the interrupts, this bit must be set high. So in case this bit is set low, but any of the interrupt is enabled, then also the interrupt will not work until unless this bit is made high. So this is a global bit. Next is undefined. Then ET2, that is the enable or disable timer 2. ES, enable or disable serial port interrupt. ET1, enable or disable timer 1 overflow interrupt. Next, enable or disable external interrupt 1. Next, ET0 is timer 0 interrupt, enable or disable external interrupt 0 is the last one. So in this way, there is each and every bit for different interrupts available, and we can disable or enable these interrupts by through programming using this software, using this register. Again, we can also set the priority. This is the default priority of the interrupts, with the external interrupt 0 is having the highest priority. So basically the interrupt that is having the highest priority is serviced first, and so on. So now this is the register in which the priorities can be set as a programmer. So we can use this register by setting the high or low to the particular interrupts to prioritize them. So this is known as the interrupt priority register. Next, the timers in the 8051. So it has got two 16-bit timers, timer 0 and timer 1. And they can be used either to generate accurate time delays or as the event counters. These are accessed as the two 8-bit registers, that is TL0, TH0, TL1, TH1, and so these are the four 8-bit timers. The timer 0, in the timer 0, it's a 16-bit register and can be treated as the two 8-bit registers, TL0 and TH0, and they can be accessed similar to other general purpose registers. Now, the instruction move TL0, #07, it means the immediate data 07 is moved to the lower order timer 0. And when we write move R5, TH0, that means the higher order byte of timer 0 is saved on to the R5 register. So 16-bit timer register is shown as TH0 and TL0 in the two parts. And timer 1, again, it's a 16-bit register, and it can be divided into two registers, TL1 and TH1, and these can be accessed like this. So this is timer mode register, and it's used to set the operating modes of different timers. Here the gate bit indicates the use to start or stop the timers by the hardware. When the gate is 1, the timers can be started and stopped by the external sources. So this bit and this bit. This whole register is divided into two parts. This part is for timer 0 and this part is for timer 1. Again, C/T bar, this bit is used to indicate to decide whether timer is used as the delay generator or the event counter. When C/T bar is 0, the timer is used as the delay generator, and if C/T bar is 1, the timer is used as the event counter. So this way, the operating mode of the registers of the timers are decided. So here the two bits M1 and M0 decides the operating mode of the timer by the following combinations. This is the basic circuit of 8051. Here we can see the basic circuit means the reset circuitry, the clock circuit, and the power up circuit. So this is the basic circuit. So it consists of mainly three parts: reset circuit, the oscillator circuit, and the power supply. So first of all, the power supply, pin number 40 and 20, that is VCC and ground. As you can see, pin number 40 is the VCC and pin number 20 is the ground. So these are connected to plus 5 volts and ground respectively. Next is the reset circuit, that is the pin number 9. Here the pin number 9 is a reset circuit, and this is provided with the manual switch also, and it also and most of them, some of the times this manual operation is not present in the circuit. So a logic high on the reset pin for the minimum of 2 machine cycles. This is the rule, will reset the 8051 microcontroller. So the reset circuit consists of the capacitor, a resistor, and a push button. And this type of reset circuit provides a manual reset option. If you want to remove the push button, then the reset circuit becomes a power on reset circuit. That is, as soon as the power is on, the reset will be done. The next part of the basic circuit is the oscillator circuit or the clock circuit, we can say. The quartz crystal oscillator is connected across XTEL1 and XTEL2 pins, that is the pin number 18 and 19 as shown in the figure. Here the crystal oscillator is connected, which gives the frequency to our system. So capacitors C1 and C2 can be selected in the range of 20 picofarads to 40 picofarads. And the next important part is the ports, port 1, 2 and 3 and 4. Port 0, 1, 2 and 3. I have already discussed these ports and their functions. So all these features makes the basic circuit of 8051. So thank you so much. This completes our architecture for 8051, and in subsequent lectures we will study the pin diagram and further the addressing modes of 8051.